So we want to do a volume by cross-sections problem that's a little bit different from what we've been doing. We want to find the volume of this wedge. In order to understand what's going on in the drawing, you have to imagine that what you're looking at is the corner of a room. Imagine you're looking into just the bottom corner on the floor, next to where two walls meet. And you take, say, a sheet of plywood or a piece of paper and you lay it against the wall. That's what you're looking at. So there's going to be a volume inside there. It's not exactly a triangle. It's not exactly a pyramid. It's a wedge. So what we want to do is find the volume of this wedge. So what I'm going to do is I'm going to do this in a particular way. There are actually different ways that you could do this, but I'm going to show you one of them right now. So what you want to do is imagine that we're stacking up triangles. If you take a look at what the bottom of this wedge looks like, the bottom of the wedge is in fact a triangle right there. And what you want to do is stack up little triangular slabs. So we have to figure out what the area of each slab is. This is the way I'm going to do this. Let's draw one triangle like that. So that's one triangle about halfway up the side of the wedge. So what I'm going to do is draw in a little bit of thickness. I'm making this kind of exaggerated just so that you can see it. Let's do this. There we go. Okay, so we have a triangular slab that the triangular slab that has a little bit of thickness, and if you notice that thickness is going in the upward direction. Well, which axis is that? That's z. So I'm going to mark this as dz because that's what we call a little bit of distance in the whatever direction. We use the name of the variable and put d in front of it. That means a little tiny bit of thickness. So what we need to do is figure out what the area of this triangle is, and it's going to have to be as a function of z. Because remember, if I'm putting a dz at the end of an integral, which is what I'm going to do, then all the variables have to be z. So I have to be able to write this distance. Let me mark it in a different color. I have to be able to mark that distance as a function of z and that distance as a function of z. Okay, so let's do it this way. Down here, if you look at the larger triangle, I'm trying to think what color. Yeah, I'll use red for this. Okay. Here's this big triangle, and as you can see, I'm just going to draw it over to the side here. Its dimensions, you can tell by the intercepts. The x-intercept is 1, and the z-intercept is 4. That means that this is 4 tall and 1 wide, like that. So this purple line that I've drawn across here, I'm using the same colors now to indicate what I'm doing. This is going to be a similar triangle. So the question is, what are the dimensions of that triangle? Well, if I pick a point, let's see, this is the x-axis and this is the z-axis. If I pick a point on the x-axis like this, let's call it x, then what you can see is that since this is going to be 0 on the x-axis, the length of this side is x. Now I can't quite do the same thing here because a height of z, if this is z, then z is certainly not giving me the height of that. It's not giving me the length of this vertical leg of the triangle. Rather, this is going to be for some point, let's say z on the z-axis. Since we know that this is 4, that means the length of that leg is going to be 4 minus z. So there we go. So this leg is x, and this one is 4 minus z. Using similar triangles, we can now set up the correct ratio. We know that 1 is to 4 as, let's see, 1 corresponds to x, so this corresponds to x, and this 4 corresponds to that expression, 4 minus z. So now I'm just going to zip through some algebra and solve for x in terms of z. And notice, by the way, that I just used cross multiplication. I used cross products to set up this equation once I had the ratio. So, all right. So we now have an expression for this leg of the triangle. In other words, this leg is going to be 1 minus 1/4 z. So now we have to figure out what this leg of the triangle is. And we do the same sort of thing. Now we're going to be looking at this triangle here. So we see that there's a right angle at the bottom. I'm just going to draw this triangle. Draw it the other way so that you can see it's a different triangle. What you can see is that this leg of the big triangle is 2, and this leg of the big triangle is 4. And now the purple line, in other words, this line that I'm trying to find the length of, this is going to be the bottom here. Note that we're on the y-axis, so that's going to be y. And then this segment here will be 4, sorry, be 4 minus z again. But we knew that because it's actually the same as this side of the triangle. In other words, it corresponds exactly to there. So we can now set up a different equation. We have 2 is to 4 as y is to 4 minus z. And now, once again, we just zip through the algebra. Okay, so now what I have is I have equations for the two legs of this cross-sectional triangle that I've drawn in here. So this is going to be leg 1, and this is going to be leg 2. I'm just pointing at them. Okay, so now we know what the area of this triangle is. We can write that in. That's the area of the purple triangle that I've drawn. So we know that if that's the area, then what I can do is I can convert this into, let's say, a volume of one cross-sectional triangular slab by simply putting a dz after it, thereby multiplying the area of the triangle by its thickness. And by the way, if you missed where this comes from, where the formula for area comes from here, we know that the area of a triangle is 1/2 base times height. For a right triangle, that means we can simply multiply the two legs of the triangle together. So that's why we have here, this is leg 1 and this is leg 2. Okay, so now we have our expression for the slab that we can integrate, and we're going to set that up. So I have the integral. I'm going to add up all of these slabs, but I need to know from what to what. In other words, what is the lowest possible value of z? What is the highest possible value of z? Well, we see that this wedge runs from a low point of 0 up to a high point of 4 on the z-axis. So I'm going to integrate from 0 to 4, and now I have an integral that gives the volume of a wedge. So we can simply evaluate this. We're going to once again just zip through all the algebra. So that's the volume of this wedge, is 4/3. Okay, I've put up the same wedge, but I've drawn a slightly different cross section. So now I'm going to ask you some questions about this cross section. And now I'm going to point to this side. Can you write an expression for the length of that side in terms of x? So in other words, your answer should only have x's and numbers in it.